I'm Zainab. I'm not going to be speaking about the currents of currency. I will be speaking about the currents of concurrency, and there is a big, big difference. Okay, well, yes. Cool. All right, so I'm Zainab. I really, really like programming languages. And in fact, I like lots and lots of different ones. So I just, this morning, thought I'd make a little collage of all the ones that I've been doing semi-recently. So I do really like Rust, of course, but I also quite like Scala. And I really like the functional programming space. So a lot of the things that we've been talking about over the past couple of days about safety, type safety, getting a lot more validation from our compiler. These are all things that are very prolific in the functional programming space. As well as functional programming, I also do quite like proof assistance. So you'll see a few proof assistants listed here. Also formal specification languages. I wish I could use more of these at work, but sadly, we've got a way to go. Now, another thing that I'm really interested in is how we think. And this is because, as well as enjoying functional programming, it's also something that I teach. So I teach functional programming to developers, some of them quite junior, some of them completely new to programming, but also some of them who are very experienced. And the way that we think about problems, think about how we solve problems, is very different depending on the discipline that we're doing. Okay, so as well as learning, or rather being interested in the way that we learn, I'm also really interested in concurrency. And you might be wondering, okay, why concurrency in particular? Okay, so in a few of the presentations so far, we've seen some examples of some bugs. Who here has had a bug in their code? Yeah, of course, right? We've written code has bugs in it. Who has had a bug in their code which only happens on the CI system? Yeah, never locally, only on the CI. What if it only happens sometimes? Yes, and only sometimes on the CI. 1 in 100,000 times? Okay, yeah, a few people. Have you ever found this bug that happens once in maybe 100,000 times on the CI, and you only know this because you've needed to repeatedly loop the thing? Yep. And you also realize that this bug is out there in production, right, in a really important system. And you're trying to find out what it is. And you can't, right? And the thing is that we think that, right, good code, good safe code is the thing that will help us sleep at night. Well, concurrency bugs, these are the things that keep you awake at night, right? They keep you awake at 4 a.m. trying to figure out what on earth is going wrong with your system so that it doesn't go wrong in production. Hopefully it hasn't. And the thing about concurrency problems is that often they can be solved in our heads, right? Not just in code. So concurrency is difficult. Concurrency in Rust is difficult. And it's also difficult in a lot of other languages. So it is by no means a new problem, right? In fact, concurrency problems have been around for as long as there have been programming languages. And each language has a different kind of solution for them. So I've just picked a few. So for instance, if you're coming from the JavaScript world, you might be familiar with the terms async await already. On the other hand, let's say that you're an experienced Go programmer. You'll have Go routines, right? Those are your solution for concurrency. So I quite like Scala, and it's got its own ideas of async programming. Does anyone know, by the way, what that logo is in the corner? Yeah, a few people, right? So that's Erlang, right? Erlang is amazing in some of its concurrency concepts. And the thing is that we think of these languages as, oh, they've each got their own concepts, their own ecosystems. But in fact, their ideas from different languages migrate. And in forming Async Rust, right, ideas migrated from a lot of different places. And so when we analyze Async Rust, when we try and learn about it, we need to also think about where these concepts come from. Now, there is a reason why there are so many different ways of thinking about concurrency, right? Each language, each ecosystem has its own constraints. Some of these have garbage collectors. They have runtimes. They make a lot of decisions for you. Others have stronger type systems. And these all influence the landscape of concurrency. Now, as well as ideas migrating, we all know that Rust has attracted a lot of developers, right? People migrate too. We start using Rust, we start using Async Rust, and we've probably come from a place which already has its models of concurrency. And that's one of the reasons why Async Rust is so hard to learn. It's because we already have some preconceived mindset for how we solve concurrency problems. And so now we need to relearn something. And we all ask different questions, right? If you're from JavaScript, right, maybe you're quite familiar with async await already, and you're actually wondering, oh, well, why is there so much other complexity, right? And if you're from Go, you're probably wondering, why doesn't everyone just use channels all the time, everywhere, right? Why do we see these other things? Okay, so we're going to learn a little bit about Async Rust. There have been a few presentations so far in which we've said Async Rust is difficult, and actually that this makes me a little bit daunted, right? Trying to explain this thing to you. And in fact, I don't know if was anybody at the Code Your Future talk yesterday, right? Yes. So I think we were trying to in that talk list all the concepts that you need to learn, right, before you can even understand a small bit of Async Rust. And we came up to a list of something that was greater than 12, I think. It was very long. Let's try and boil it down into just 3 broad concepts. I'm not going to tell you what those are. Let's reduce the cognitive load. We'll encounter them over time. Okay, so in order to learn about Async Rust, let's first take an example. And I'm going to take a toy one. It's a very basic one, and that is this slideshow. So in order for me to present this to you, I had to do a few things. First of all, I had to log in to my laptop. I had to open up a session. I'm then actually serving this locally, so I had to start a web server. And I also had to open my browser. And after I'd done those 2 things, I'm actually presenting, right? I'm presenting my slideshow. So I've drawn these up, these tasks. In fact, let's not use the term task. Let's use the term unit of work, because task already means something in Rust. I've drawn these up as boxes. And the most interesting ones here are the browser and the web server, because those are side by side. And by side, what I'm trying to show is that those are concurrent. But I've not told you what concurrency is, right? It's in the talk title, but that doesn't mean that you know. So when we talk about concurrency, when we think about concurrency, what we're really thinking about is doing 2 things in a fuzzy way at the same time. But what we really mean by that is in any order. I'm not really starting my browser and my web server quite exactly at the same time. I might start my browser first and then start my web server, or I might start my web server first and then my browser. The key thing here is that the order doesn't matter. These 2 things are independent of each other. Okay, so what we're going to try and do is that we're going to try and code up this concurrent program in Rust. First of all, let's code up the one that we've seen. just this basic four unit graph. And after that, let's try and make this more general. Let's see if we can try and code up something that will run any graph of units. And along the way, we'll encounter different concepts. Let's try and add those to our map of concepts, both our map of languages and also our three broad concepts. OK, so let's just, to understand where we are, let's try and solve this problem with no async Rust. Let's just write some basic Rust. So here's my main function. It's going to start four things. It's going to log in, start a browser, start a web server, and start the slideshow. And this is just a toy example, right? So my start function, all it's going to do is print and sleep. So we'll print that we are starting something. We'll sleep for about a second, and then we'll print that we're actually running it now. Note that I've simplified this code, right? So I'm removing a lot of calls to things like clone. So yes, if you're a reasonably experienced Rust developer, look at this and kind of insert all the symbols and functions. OK, so here's our output. First of all, we start login, and then we're running our login. We start our browser, run that, and then start our web server and run that, and then start our slideshow and run that. And that's all completely sequential. If I was to demo this, you'd also see that there would be a 1 second delay between starting and running being printed. OK, let's try and write this using async await. I can introduce a couple of keywords. I can write async before main and start. And now I can write await on each line. And instead of sleeping, let's use this delay, which will delay for a second. So we're now using async await, right? We're using concurrency. And this is what we get. We get the exact same thing, right? So so this code is also completely sequential. So what have I done, right, in introducing this async await, aside from make my code slightly more verbose and possibly less performant? Well, I'm starting to think about it in a slightly different way. So instead of thinking that my code is always a series of steps, I'm now describing my code in terms of these units and also how to compose these units. So you can think of the async keyword as introducing one of these units that I'm trying to compose. And you can think of await as sequential composition. So when I write await, what I'm trying to do is sequentially compose things together. And in fact, I can look deeper into one of these units. Let's look at the one that starts the browser. And our start function, right, it was doing three things. It was printing, then delaying, and then printing again. And so actually, each of these things is composed of 3 units as well, and those are also sequential. Now, it just so happens that when we write most code, our code is always sequential. So we're always doing this kind of sequential composition. But now, when we write async await, we're thinking about it a little bit more explicitly. And that's because we don't actually want sequential composition, do we? Right? We actually want the browser and the web server to run concurrently. So even though we talk about async await as these really important things, the async and the await, those aren't actually the most important things. The most important things are the other primitives that we have, which will allow us to compose concurrently. So there's one thing that we can use for concurrent composition, and that is join. There are also other ways, I should say. But one way of thinking about join is that we now have 2 units, right? Start of our browser, starting our web server. And we want to declare that, okay, we actually don't care about the order of these things. They can run at the same time. And so we can use join to do that. So join is actually a more important primitive than async await here, because it's allowing us to do that concurrent composition. So this is how we use join. And if we do use it, we see that now we are starting our browser and web server, and they are happening at the same time, right? So we're not running our browser before starting our web server. Okay, we were talking a little bit about concurrency bugs and them happening sometimes. Will I always get this output? What do we think? No. We're seeing a few people not sure, but a few other people saying no. So if I was to run this again, it might be that the web server started first, right? If I was to run this in a very, very weird environment, maybe actually I would see that the browser would start and run before the web server would. That would be a weird environment because we have put a delay of 1 second in there. So this is one of the problems that we have in concurrency, right, is that we don't always have determinism, and we need to start thinking and reasoning about our code a lot more because of it. So composition is actually a really big concept in async programming. It's one that we never really talk of very much because we always talk about the keywords, right? We never really take a step back and think about what we're actually doing. But if you start thinking about the world in terms of composition and start thinking about your problems more on paper than in code, then a few things start to make a bit more sense. Note that when you talk about composition, you don't talk at all about the way that things are run, right? What you're talking about is how things relate to each other, right? Your dependencies of units on other units. So these ideas of composition, they come from a variety of different places, but largely you can see them in the functional programming ecosystem. You can see them a little bit as well in the JS ecosystem. By the way, I should say, like, we're simplifying things and saying we're tracking ideas, and ideas come from languages to other languages, right? They, the way that concepts evolve and proliferate is, of course, a lot more complex than that. Okay, so our aim is to start a graph of these units. We've already started our slideshow graph, so we're good. We're halfway there. Next is, let's just try and do this for an arbitrary graph, and how hard can it be? So first, let's model this. Let's model this graph. We're going to model it as just a struct which has a name and some dependencies. And we're going to have a big collection of these. And then we are going to write a function called startGraph, which is an async function that's just going to go and it's going to start this graph. Let's assume that we always give it a good graph, right? We're not going to be malicious and introduce things with cyclic dependencies. And in fact, to keep things simple, let's just try this out with our slideshow graph. So we have a unit for slideshow, and that's dependent on our browser and our web server. Our web server is dependent on login, and our browser is also dependent on login. So that's how we might code up the same graph that we started with. And let's try and draw this. So this is what this might look like in terms of composition. We have our big start graph unit. And if we want to start the slideshow, we're first going to start the browser and the web server, and then we're going to start our slideshow. Okay, so let's try and fill in the body of this function. First of all, given a name, let's just pluck out the unit from this collection of units. What we want to do is take all of its dependencies and then go and start those, and then we want to start the unit. How do we start each of those dependencies? We could use join, but we've seen join only works for a fixed set of things. We could try and use await here, but that wouldn't quite work, and it's not really what we mean. So in order to figure out what to use, in order to phrase the question properly, we actually need to dive in a little bit more into what an async function is. So far we've seen its syntax, right? We've seen how it can express dependencies, but we haven't actually gone into any details about how it's implemented. And it's actually not that complicated. So async is in fact just a keyword which desugars into some quite standard Rust code. So an async function is just a normal function, but it returns this thing which is called an implementation of a future. And a future is a trait that describes this unit of work that we're talking about. What an implementation of future, what this means, right? What we're trying to say to Rust is, hey, go and create a data structure, synthesize a data structure for this piece of code that we're writing, which corresponds to a future. Now, we don't know what this is called. We're asking the compiler to come up with a name for it. But it is something that is of a fixed size. So it is still fairly standard. And the way to think about this is that, it's just some data. So because it's just some data, we can manipulate it as such, right? We can, in fact, take this future, which is returned by our start function, and we can have a collection of them, right? We can iterate over these futures. And so now the question that we want, right, that we're trying to phrase is, okay, well, if we have now a collection of futures, how do we join all those futures together? And if we phrase that question, we can then find that there is a function, join all, which will go and help us join those things. Okay, so we have another concept here, which I'm going to term allocation, but it's actually a little bit more broad than that as we start to fill it in, which is to try and understand, okay, how are these things, these units of work, how are those laid out in memory? And this is a very important thing to understand because it helps us search for the correct primitives that we want to use when we are composing things. Okay, so we've used join all now to start an arbitrary graph. But have we really? Well, I can tell you the code compiles. The code compiles. And this is what we get out of it. Is this working? Maybe, not sure. Okay, so we're starting our browser, starting our web server, and then our slideshow. That's all okay. But I haven't logged in, right? I haven't logged in. So actually, there is a bug here in that we're calling start, right, to start a dependency. But our dependencies have dependencies too, right? We need to start those. Now, if you're working in another language, you might think, oh, well, that's easy, right? We just recurse, right? We just call start graph again. We've called it once, so we can call it again. But in fact, it's not so easy. And thankfully, the compiler does help us and tell us that there is something wrong here. it tells us that there is a recursive async function that must be rewritten to return a boxed dyne future. And it does give us a much more helpful message, which is to consider using the async recursion crate. So one of the unfortunate experiences that we have in Rust, particularly when we're doing async Rust, right, is that we do have a very helpful compiler, which is helpful enough to give us these messages. At least it's telling us that we're doing something wrong. But unfortunately, the messages that we're getting can be very different to the way that we're trying to think about the code. And that is because the Rust compiler, it understands things in terms of its core primitives, right? Its core primitives meaning the box and the dyne feature. It's not got the idea of async await actually baked into it, right? So it can't give us more helpful messages. And what that means is that in order to actually try and decipher these messages, right, to try and understand what the compiler is telling us, we actually need to understand some quite advanced concepts in the way that data structures are modeled in Rust. And that's because this future is actually quite an advanced data structure. Okay, let's try and think about it a little bit more. Let's see if we can try and understand why we're having this problem. We have this function startGraph, which we've said returns some implementation of future. And we've said that's a struct which has a fixed size, right? We don't know its name. We're telling the compiler, OK, go and synthesize this. But the compiler knows how big it is. But on the other hand, when we actually introduce recursion, it's no longer quite a fixed size. So has anybody tried actually to use recursion in other forms? Have you tried to write, for instance, a linked list in Rust? Yeah, so as soon as you try and write linked lists, right, you hit into this very same problem, and you start needing to use something called a box. What you find is that when you have something which is a recursive data structure, you can no longer put it on the stack because it doesn't have a fixed size, and so you need to actually play around with the heap. And you use a box to reference data on the heap. Oh. And with a box, we can construct something which is a fixed size. And that means that we can now use it. You might be wondering, OK, why did we not see this error message when we started to use join all, right? That was actually OK, wasn't it? We used that fairly straightforwardly. Even though we had a collection, right? We had something which, under the hood, had boxes. Why did we not see this error message? And that's because this join all operator, it did all of the heavy lifting for us. So underneath it, if you were to actually look into it and look into its gory details, you would see boxes, right? You would see rather complex type signatures. But it's actually kind of obfuscating that from you. It's hiding it from you in a way that's quite nice. So what is quite nice about this is that if we have the right operators, right? If we can go and search for the right things we need when we're trying to compose, then we no longer need to go into the world of boxes and dyne features, and there are more complex and hairy things, which we'll see very soon. So maybe that's where we should be going towards. Maybe the hope is that actually, as users, right, all we need to do is just kind of pluck these operators out of a library, chain them together, group them together, and not really need to worry about the implementations. OK, so if we do this, we actually get a more confusing message. We get the trait unpin is not implemented for dyne futures future. OK, so now we need to start talking about pinning. Pinning is another concept which you find when you are dealing with very advanced data structures in Rust. And those are self-referential structures. it turns out that when we wrote our future with our async await code, and it all looked very simple, we were creating something that was pointing into its own memory. It was self-referential. The problem with pointing into your own memory is that you can't actually be moved around without invalidating yourself. So that means that when we're working with futures, we unfortunately encounter this quite advanced concept, which is pinning, which is what tells the compiler whether things should or shouldn't be moved. So we can resolve this error message by creating a pinned box. But there was a much easier thing that we could have done in the beginning, which was to use our async recursion crate and just use the async recursion macro. And so that's another good thing about Rust error messages, right? Is that maybe we don't need to read the more complex part. We could just skip to the simple solution. Okay, so boxing and pinning, those are also concepts that relate to allocation. They are something which are very hard to learn because they are unique to Rust, right? You will not find the term pin, at least not meaning the same thing, in any other language. And that is because of the rather complex way that we need to visualize and model memory when we're working with Rust. Okay, so now we have started an arbitrary graph. Or have we? Okay, so this is our output now. Have we solved our problem? No. We've introduced, well, we solved one bug, but we've introduced another bug. So now we are starting this dependency on login. We're starting it twice. Okay, and this is actually where our problem gets really, really hard. We need to keep track of whether or not we have already logged in. We need to start dealing with state and mutable state. And okay, let's do something which it won't work, but let's try and do it anyway. Let's keep track of some mutable state, which is a list of all the units we've started. Okay. So if we start a unit, what we can do is we can try and add it to this collection, this vector. And then when we want to start a new unit, let's figure out if it's already started by just querying this, seeing if it's present. And if it's not present, then we can start it. And if it is, let's just skip over. Does this work? No. This time, our compiler is catching an error, which is a very valid one, right? It's a bit confusing, though, right? Cannot escape function mut closure. Okay, so if we look here, we see that we have our started units, and we're referencing it in multiple places. And if we were to actually run this, and it wouldn't be in Rust, right? Let's say that you were to run this in a different language, which didn't have your compiler helping you out. You could encounter data races. You could encounter a lot of different problems. So it is correct that we get this error message, right? It is correct that our borrow checker is helping us out, that is telling us, actually, no, you're trying to do something that you really shouldn't do. In fact, this error, it doesn't really have much to do with concurrency, right? It's much more to do with closures. But it just so happens that when we write concurrent code, we're actually writing a lot of closures. Okay, so there are two methods, two approaches to dealing with state. And so far we've kind of said, okay, everyone's on friendly terms, right? All of our different ecosystems, they all share things from each other. They all go on holidays, right, to different languages and go back. But actually there are some things which are very contentious. And that is the way that state is handled. So on the one hand, if you're coming from JavaScript, you share state. You share state a lot. You share state all over the place. On the other hand, if you're coming from Go or Erlang, you don't. You don't share state at all. Rust is neutral territory, right? We're neutral territory. We can do both if we want. You know, I think the fact that neither side has actually won this argument yet, the fact that we don't look around and see all languages doing the same thing, all ecosystems doing the same thing, it probably means that they both have their merits. So we'll look at a couple of approaches. Right, one is we're going to look at mutexes. Okay, so we can't use mutable references. We can't use mutable references for a variety of reasons, but we can use something else, which is known as a mutex. So a mutex is a bit like an all-powerful construct for dealing with concurrent mutable state. It's not always recommended, by the way. Don't take it as a recommendation. The only thing that you can do with a mutex is lock it. So it's something which wraps your state up and lets you lock that state. And when you say lock, what you really mean is, okay, nothing else can access this thing. I'm the only thing that can access this piece of state. And that means that you can safely update it. Unfortunately, because of the nature of how you use mutexes, the borrow checker can no longer help us. So we need to do something called reference counting to track how our mutexes are used. Okay, so reference counting means we're using this thing called an arc. We're using it to wrap our mutex. It's one of those other concepts which we're now adding in. Okay, so now what we're going to do is that we're going to lock our state to get our started units, right? So nothing else can touch our list of started units. And then we can now check, right, if it's got the unit that we're trying to start. And if it has, we do nothing. If it hasn't, then let's try and start our unit, and we'll add it to this collection. Okay, what do you think we get? Have we solved our problem? No. No, this is what we get. Yeah. This is our first deadlock. And debugging deadlocks is very, very difficult. So let's just put some print statements in. Maybe we'll try and understand what's happening. Okay, so we're trying to acquire a lock, first of all, for slideshow. That's the thing we're trying to start in the beginning. And we get that lock. And now we're trying to start its dependencies, right? Browser and web server. So, okay, we try and acquire the lock for browser. But slideshow already has our lock, right? We can't acquire it again. So this is one of those problems which we could have actually solved on paper, right? If we started to draw out the order of work and the kinds of work that we were doing, we would be able to see that, in fact, we were locking. And then when we tried to start our browser and web server, we were locking again. So this is a problem that we would be able to spot if we actually just started thinking about how things were composed. There is a solution for this, right? Which is that you just we can unlock, right, by dropping our state. But in order to explore both camps, right, let's move on and take a look at the other approach, which is don't share state. Okay, can we solve this problem without sharing state? And if so, how? Okay, so the way not to share state is to create something called an actor. Now, an actor, you can think of an actor as a bit like a future, but it is a future with its own internal state. And it doesn't pass that state on or let anything else access that state. It can send messages to other futures, other actors, and it can receive messages, and it does that via channels. It never has synchronous conversations, though, right, these actors. They're always asynchronous. So that's a bit of a problem, because you can send a message from one thing to another, but you can't actually always expect a reply, right, because of the way that these systems are designed. Okay, so this is how we create an actor. Right, we use channels. Channel is a mechanism for sending and receiving messages. It's split into two parts, a sender and a receiver, and these two things can be owned, right, by different features. So the sender, right, can send a message, and the receiver can receive a message. It will receive the message that was sent. And depending on your sort of channel, you can have multiple senders. Right? So you can have multiple senders and a single receiver, and that's kind of what we want to try and do here. Oh gosh, where are we? Yes, it would be easier with the keyboard. All right. Okay, so this is what we want to try and do. We want to have a system by which we have an actor, and that's going to receive a message, which will be to try and start something. And we're going to have a few different senders, which are the things that are actually doing the starting. Okay, so here's what our system. We need another component. We're going to call this an orchestrator. It's going to be the thing that goes and starts everything. And there's only going to be one type of message, and it's just going to be the name of the thing that is being started. Okay, so let's see what our orchestrator might look like. Okay, so we get a message. Our message is the name of the thing that needs to start. And our orchestrator, this is going to be the thing that has the state. It's going to have some state which it's not going to share. It's going to have some state which corresponds to the units that have been started. And okay, so we can now check, right? If that state contains our unit, right, then we don't need to start it. Otherwise, let's try and start our unit. And now our start graph function, right, it's going to do the starting. But before it starts, it's going to send a message to the orchestrator saying, should I start? And it's only going to start if it gets a reply. Okay, so I've used some terms here which are already a little bit dangerous when you're talking about actor systems. I've used the terms reply. I've used the terms ask. That means that I actually do want some communication back. And creating that kind of that communication needs another channel. So we actually need to explore channels a little bit more. We're going to create something called a one-shot channel, which is something that will let us send one message. And one-shot channels are perfect for situations like this, where we want to receive one message back from our orchestrator. As well as getting the name of the thing, let's also get this one-shot channel. And now in our orchestrator, once we actually go and oh wait, no, this in our start graph function, right? So once we send a message to the orchestrator, let's also send this one-shot channel over, and let's wait for a response. When we get the response, we'll start our start our actual unit. Okay, and our orchestrator itself is quite simple, right? Because it's either going to send a true, right, if we want to start, or it's going to send a false if we don't. There's actually an even simpler way of writing this, and I'll leave that for an exercise. Okay, and so now this is what our main function might look like. We now have this orchestrator, which is an extra component, and we need to compose that. So one way of composing that component is to use join. So if we were to draw out our system, this is what it might look like, right? We now have our orchestrator, right, which is a unit of work, right? It's a unit of work which is running, and it's running concurrently to whatever is starting the graph, okay? We have some things, such as sending and receiving, in which there is a dependency, right? So sending is going to happen before receiving. So we know that there's an order of operations here, and we can start to think about those. So even though we've got this quite complex system now, we can actually draw it out on paper and still figure out if there are any concurrency bugs. Okay, so we've talked about shared state. That's our last concept, right, is how we share state. So channels and actors, those kind of come a little bit from Go, but they really come from Erlang. And Erlang is the language which kind of has the best tools for working with actors. Okay, now, actually, yes, we have solved our problem, right? We do get the output we want, which incidentally was the thing that we had in the very beginning, right? But now for an arbitrary graph. So, it's good. Okay, so we've had a whirlwind tour, right, of Async Rust. We've looked at lots of different languages. We've looked at lots of different concepts. There are many, many more concepts, by the way, on this map, right, that we haven't explored, right? I haven't talked at all about runtimes. I haven't talked about when you should not use join, right? I've introduced it, but I've not really talked about it. I haven't talked at all about green threads. What about error handling, right? There are so many things that could go wrong here, but we've not modeled them. There's even more things that can go wrong in the case of concurrency, because sometimes you want to cancel stuff. We've not talked about cancellation at all, and that's a very difficult problem. But nevertheless, I encourage you to try out Async Rust, right? Try out a few resources here. You can take a look at the Async book. I also really like the Tokyo docs. So go have a look, play around with those. If you can, try out async programming in other languages, right? Try it out in Erlang, try it out in a functional programming language like Scala. Come back and see what concepts you can relate back. And if you want to contact me, you can find me on LinkedIn. You can also send me an email. I would love to hear your stories as well. Reach out to me today. If you're interested in functional programming and you want to learn a little bit more about that, I'd be very, very happy to talk to you. If you're interested in reasoning about concurrency, or any of the other languages, in fact, that were on the first slides, then please come speak to me as well.
Thank you, Zainab. Okay, we got 5 minutes for questions. What are your questions? Yes.
So, regarding the graph, assuming that we have, I don't know, it should be a direct acyclic graph, okay? So, could be an idea instead of doing what we saw, something like making a topological sorting and starting from the nodes with the less incoming edges, so that we can just run the one without dependencies and then scale up. Could that work also? Could be an alternative?
Yeah, yeah. Okay, so the question is, let's go all the way, something like this. Oh, where's it gone? Beginning. Here we go. Okay, so can we take this graph, if it was an arbitrary graph, right? And instead of trying to solve this recursively, could we come up with a different sorting algorithm? So beforehand, right, take our data structure, which was, let's say we were modeling this as a vector, create another one, which would just have potentially like the order of things that we wanted to start, like at different levels, right? Yeah, I think you could, right? There's nothing stopping you from solving it that way. And then what you would come up with, right, would be a series of tasks or units, right, that you wanted to run concurrently at each level of that structure. Yeah.
Other question? Yeah.
Is the cancellation solved in any language?
It depends what you mean by solved, right? So cancellation. Let's say that we wanted to do something else, right? Here I've said I want to start my browser and my web server. What if I wanted to start either one, didn't matter, maybe both, and I just cared about the first one that came back, right? You know, I have two things that. Okay, let's come up with a different example, right? Let's say that I want to go. You have. I pick two of you, and I tell one of you to go and get me some food from the shop outside, and another one to go and get me some food from the restaurant. All I care about is that I've eaten something, right? I don't actually care which person comes back first. And let's say one of you comes back. I might want to tell the other one, hey, no, you don't need to go. You don't need to keep doing what you're doing. So that's what we mean by cancellation in a concurrent environment. The question is, okay, has this problem been solved? You always have to think about whether you want to cancel something or not. There are different methods of handling your resources on cancellation and making sure that cancellation does occur. In some runtimes, such as, for instance, if you were using various libraries in Scala, you would have cancellation all handled and sorted for you. That's assuming that that's what you actually want, right? So assuming that you want to cancel the thing, it would go and perform all its cleanup. It's more complex in Rust, right? I wouldn't necessarily say it's solved or not solved. It's more it's something you need to think about. On the other hand, let's say that you're coming from a language like Erlang. There's not necessarily in-baked cancellation, right? It's something which you have to encode, right? So you, in designing your system, now need to design the plumbing for how that system is cancelled and what cancellation means, right? Because it means different things, right? I hope that's answered your question.
Okay, we're out of time, so if you have other questions, you can meet Zainab during the breaks. And yeah, Zainab Ali!